Okay. All right. I turn the volume up a little more here. I guess maybe in the back it's hard to hear for some people. So again, let me know if you're having trouble hearing or seeing anything or anything like that. Um, but yeah, so we're September 10th. We're right here, basic language features. So we're going to finish off our introduction and talk about basic language features. Tutorial 1 has been released. I've seen that some people have done it already. Basically, you're going to be poking around the command line. Yep. Oh, really? You don't see it? Oh my goodness. Uh, okay. I'll take a look at that after class. I'll see. I probably there's a setting somewhere. Maybe I messed it up when I set it up. Hello? Yeah.
So on the tutorial for I think question 26, there's like a command that was in there. When I type it in, it didn't work. And I was like Googling why, because I had a friend that had the like same issue where it just wasn't working.
Right.
And it was with like the wall command. It said to like swap where the dash O and the dash wall was. And then I put that in and it worked. I don't know if it was wrong on the tutorial or like
Oh, okay. I'll look into that. I mean, great that you bring it to my attention. Stuff like that, I'll generally just adjust the marking so everybody gets the mark. So, yeah.
For the tutorial, do you want us to use on general assignment COMP2401 F24 or F23?
Whichever one you want. So yeah, there is so they did release a new version of the virtual machine, and it is it's upgraded to the next, I think, Ubuntu 24 whatever, which also includes the next compiler, right? So the numbers that are in the slides are not going to be the ones you see if you use that virtual machine, but either of those is fine, right? Again, at the level that we do see, not a lot changes, and especially not just from a one version upgrade to the next. It's not going to make any difference. So yeah, sorry, question 26. And there was and other also the quiz is gone, right? So is that the only two things? All right, I'll figure that out. There's probably some Brightspace settings. Brightspace has a million settings, so my apologies. I'll get that straightened out after. Yeah, let's write that down too. Okay, any other issues? All right. So yeah, these should be low stakes quizzes, right? So again, if there's trouble, I have no problem usually extending the deadline a little bit or whatever. This is just to get you engaged with the material, and you're going to learn a few like interesting things about C and the command line. Also, assignment 1 has been released. It's just basic C programming using arrays and input and things like that. So yeah. I'm not going to go over it in great detail. I think we have a lot to cover today, but any questions or comments on the assignment? Okay, so the first thing I'm going to do is last time the setup I used was, well, I forget what did I use. Virtual machine. I used the virtual machine. So this time I'm going to, for those of you who have a Mac, maybe the virtual machine is not an option. I'm going to show you OpenStack. So I'm not going to go through the whole thing. You still have to set up your own OpenStack. But I'm telling you, it's very easy. If you go to the, if you Google Carlton OpenStack, and then Andrew made a lot of nice videos. It'll take you about 10 minutes, maybe the first time to set it up. And then you'll have an OpenStack instance with a public IP address that you can, it's a server, and you can SSH into it, right? So SSH is the secure, I forget what it stands for. And maybe somebody knows. What's that? Oh, shell? Secure shell. Secure shell. Is that what you said? Yeah. Okay, secure shell. That's very plausible. That's probably it. I don't know. But so we're going to SSH into OpenStack. And so I've opened PowerShell here. Any shell will do. As far as I know, I at least have tried every shell that I've tried so far. If you have a Mac, it's gonna be fine. If you have Linux, it's gonna be fine. If you have Windows, it's gonna be fine. The PowerShell lets me also use some Linux commands, so I kind of like it. But So what I'm going to do is I'm going to SSH. So when you set up OpenStack, you're going to assign it a public IP. You just choose one, and then you're going to copy that IP, and you're going to write SSH student is your username at, and then the IP address. So mine is this. All right, so the first time, after we're going to connect to it using VS Code, right? So it's a really nice way to work, and it's basically like working on your own machine. But the first time you connect to OpenStack, you have to do it. You can't do it through VS Code, or if there might be a way, but the way that I usually do it doesn't work. So you're going to have to go from a shell. So I SSH in. It asks for my password. The first time, the password will be student also. Okay. So here you can see I've signed in. When you go for the first time, it's going to say that you need to change your password, right? And the reason being because it has to be secure. If everybody knew that the password was student, then all you need is my public IP, and you can connect to my OpenStack and then do whatever you like. So when you connect for the first time, you're going to put student, and then it's going to say, please tell me your new password. So you're going to put that in twice, and then it's going to disconnect you. Okay, and then from there, you can sign in again, or you can sign in using VS Code. Okay, so questions so far? Okay, so now we're going to take VS Code, which I imagine most of you will be using. Again, you don't have to. You can actually just, use Vim or something from here. But what I'm going to do is I'm going to look at extensions, and I'm going to search for SSH. And this remote SSH extension, I'm guessing it'll still work, but I might have to restart it. The remote SSH, and then just click install, and it'll install for you. Okay, and then once you've done that, now basically behind the scenes, VS Code is going to do exactly what we just did with the shell. It's going to SSH into OpenStack, but then it's going to communicate with OpenStack and grab all those files and just display them in VS Code instead of either in Vim or whatever. So once you've installed the extension, then you can go down here. There's other ways to do it. This is the way that I like. And then there's a bunch of options. So this connect to WSL, that's another extension that I installed. We're going to ignore that. Connect to host or connect current window to host. I'll select current window. Now, the first time, your IP address is not going to be here. So you're going to have to add a new SSH host. And what you're going to put in is the exact same command that you already put into your shell. So this SSH command. Okay, so I would put that there. And then I would press enter to confirm. It'll ask where you want to save it. Maybe it'll ask me. Yeah, so it's going to say, should I save it here or here? So if I save it here, this works for everybody. If you save it here, this only works for your user profile. Either one is fine. All right, and then so now it's closed. So now I can open my SSH. So this is just a list of the connections that I can SSH into. Since I doubled up on that one, I'm going to get rid of it. And then the next time I go to connect, the IP address is going to appear. I'll just select it. It's going to ask me for my password. That's the new password that I made. I like literally when I'm typing it, I want to say it. And so now I'm in, sort of, right? I'm almost there. So I still want to open a file or a folder or something. So by default, it's going to open to student, but I actually want to make something. So in documents, you can see the other two classes that I teach, I made some directories. We will just open in documents for now. And it's going to ask me for my password one more time, and then I am in. Okay. So yeah, questions so far? Okay, so now I'm connected both with PowerShell and with VS Code, which is kind of how I like to run things. I am going to. All right, so now I'm in the same folder in VS Code as I am in my shell. I'm just going to make a new directory. Did I use, yeah, COMP2401. And then I will CD into. Okay, so now I'm in this directory. There's nothing there. But what I can do is I can take, now it's really easy. I have this test folder that we were using last class, and I want to work on it here. I'm just going to drag it and drop, and voila, all that code is there. You can see that I compiled it. I'm just going to delete this because that's a Windows executable, which I don't want. And now I can try my hello world again. So I'm going to okay, so now I've compiled hello world and I can run it. Hello world. So you can see that the files are being added, and I'm running from my terminal, and all of this is happening as if these files existed on my computer, but they're actually running on a server in, I think, Hertzberg, but maybe somewhere else. And then I can modify things and do whatever. Okay, so that's a nice way. If you're using a Mac, this is going to be, this will work great, right? This works great. When we get to graphics, you might have to, you might need a interface that now uses a desktop, right? So there is one. I think I don't be Go, but they changed it this year, so I will find that information for you. And all it's going to do is basically the same thing that VS Code is doing. Is it's going to communicate over SSH, but it's going to pass a lot more information back and forth. It's going to recreate the desktop for you, right? So then you can use graphics like X windows and things. And it's going to be a little slow, but it will work. Okay, questions? Yeah.
Can I make a shared folder?
Yeah, but it is pretty easy to, yeah, you can't have a shared folder, but I can download it easy. So I can drag and drop and upload them and then just download them. And so you have to do it. Well, probably there's a way to, there's an extension for everything, right? But you can manually do it as well. Yeah. What's that? No, this is nothing to do with the virtual machine. So if you're running a Mac with an M1 or an M2, the virtual machine, at least VirtualBox doesn't work. So you can run parallels, but that costs money. This is free. If you have Windows, you can do this or the other one, or yeah. So the other, if you have the virtual machine and it works, by all means, you can stick with that. That's also a very good solution. All right, other questions? Okay. Last class, we did do the hello world, and we talked a little bit about compiling. So compiling into object code and compiling into, well, we compiled into assembly, I guess, and an executable. So now we're going to continue talking about, well, we're going to do a little detour. All right, so yeah, so one thing to make note of, so you won't have this problem on OpenStack, and I can't, honestly, I'm setting up 3 classes that are all doing like similar things right now, so I can't remember what I have told you and what I told the other classes, but Windows file systems are not case sensitive, but Linux is, right? So if I have 2 files, one with a capital R and one with a small r, if I'm using shared folders, these are going to look the same. They're both going to compile fine. Whatever I do is going to work. If I'm using OpenStack, and it's now this is actually a Linux file system, now these are going to be different, right? So this is something you might run into. Yeah, I guess we're not really using Gradescope. We might at some point, but the TAs might run into this problem, right? If they're running on a pure Linux machine and you submitted code that you compiled on a Windows file system, even though you're using Linux, they might have trouble, and you will get a small deduction for that. As long as they can fix it, there will be a deduction, but it'll be small. So try and keep that in mind. Debuggers, I'm not going to get heavy into them. We might look at it a little bit later, GDB, but it is sort of a heavyweight. It's good for big programs in some sense, but print statements work just as well for debugging, right? So when you're debugging, basically what happened is almost 100% of the time somewhere, some variable got corrupted. So you have some bad value and that caused a crash. Maybe you have a or maybe you walked off the end of an array, you accessed memory you weren't supposed to, but even that's sort of a bad variable, right? So what I want is, in order to track down the bug, I want to see the variables at each step of my program. And to do that, I can use print statements, or you can use GDB. It works pretty good. Again, though, GDB is pretty lightweight also, but it's still way heavier than print statements. But we might take a look at it later. All right, so given that we've compiled a few Hello World program into object code and binary, and we talked a little bit about what that was, assembly, but now I kind of want to give you a slightly better idea of what it is. So we're going to talk a little bit about computer organization. We're not going to go very deep. You can teach a whole class on this stuff. But we're going to talk a little bit about what a computer is, how it works, and we're going to see a small, very simple assembly program, just so we get a good mental model when we're talking. Because when I'm talking about C is very close to assembly. And so if you have a good mental model of what a CPU does, then these things will make more sense when I try to explain them. So a CPU basically looks like this. We have a control unit. This controls what code is running. We have a logic math unit. This will do logic and math. And we have a bunch of registers. These are just memory that is very close, that's just right on the CPU, right? So they can store temporary variables and work with them. And then what they do basically is you read in memory from RAM, and then you store it in a register, you do some operations on it, maybe you add, multiply, whatever you want to do, and then you write it back out to RAM. And that's essentially all a CPU does, right? You can do a lot with that though. And it does that like maybe a couple billion times a second, right? So it's very fast, but, and yeah, so one of the reasons why registers are on the CPU is, well, to make them fast, you want them as small as possible. Right, so this, again, I might be repeating myself, but electricity travels at the speed of light, or at least the signals do. And but twice as far is still takes twice as long, right? So the smaller you can pack all this in, the better, or the faster. And that's it. So reads a value in, does some manipulation, writes a value out. That's all your CPU really does. So we're going to look at an even simpler CPU and a simple program on the CPU. This CPU, we're going to have 3 registers. So these little pieces of memory, an instruction pointer, which will tell me which part of which memory location I should get the next instruction from, the instruction register, which is going to store that instruction, and an accumulator, which is just some multi-purpose math register. It's going to keep track of some numbers for it. And then we're going to do what's called the fetch, decode, execute cycle. So fetch, decode, and execute. So we're going to fetch an instruction from memory. We're going to decode it and then execute it. And so what is an instruction? Well, I have RAM. This RAM has a bunch of memory locations. And in these memory locations, I'm going to store values. And we're going to talk a little bit about how we interpret values in C, right? These are all just bits, right? So these are basically a series of zeros and ones, which are high and low voltages. At the end of the day, they're just a bunch of wires. But these represent numbers, and these numbers, when loaded into the CPU, represent instructions. So here, for instance, I have the instruction load 6, which means load the value from memory location 6. Okay, so we're going to start. And this is all based on, just to give credit where credit is due before I forget, this is based on a video by Tom Scott. There is a link there, but I can't, using Zoom for whatever reason, it doesn't let me click on it, but if you download the PDF, it should be there. And this is basically his example. I just found it really nice, simple, but very sort of complete illustration. Okay, so let's do like at least one cycle, one revolution of this program. So the first thing I'm going to do is I'm going to grab the instruction from location 0, right? So that's this load 6. And I'm going to grab it and I'm going to load it into the instruction register. Okay, so that's the fetch part of the fetch, decode, execute cycle. The next part is decode. So what happens now in a CPU is the CPU actually, these are sort of a broad instruction set like assembly. A CPU is going to translate that into what's called microcode, which are a bunch of instructions that it understands. A lot of that is proprietary, so you're not going to find a microcode manual unless you work at like Intel or something like that. As far as we're concerned, software engineers, assembly is basically as low as we get in terms of programming. Microcode is the hardware guys. But this will get translated into what the CPU should do. And what the CPU should do is look in memory location 6 and load the value there. So we've preloaded it with 1. Also 7 is preloaded with 1. So what it's going to do is it's going to grab that value and copy it into the accumulator. Okay, so that's our first instruction. This is the execute part of the fetch, decode, execute cycle. Okay, so we've done one complete cycle, and I didn't mention it, but the instruction pointer was incremented, either just after we complete the previous instruction or just before we go to the next instruction. It doesn't matter, but now it's pointing to location 1. Okay, so we're going to do the fetch part, which means we're going to grab this command now, which is add 7. We're going to load that into the instruction register. We're going to decode this and also increment the instruction pointer. So when we decode this, this add 7 means grab the value that's in location 7, which is a 1, and add it to whatever's in the accumulator. Okay, so then on our execute, we're going to do exactly that. So we're going to take 1, add 1, and we get 2 in the accumulator. Okay, so that's one more revolution of the fetch, decode, execute. I go back up to my instruction pointer. It says look in location 2. This says store 6. I'm going to fetch this instruction into my instruction register. Now this says write the value of 2 into location 6. So I want 2 to go here. That's the decode part. Okay, so decode. We're going to look at location 6, and we're going to write the accumulator value out. So now on the execute part, we do exactly that. So we've read in a value, we've manipulated it, and we wrote it back out. And yeah, then we go to our next cycle, and the instruction is pointing to 3, which is a jump 1. We're going to fetch it into the instruction register. We're going to decode it. When we decode this instruction, it basically says write the number 1 into the instruction pointer register. Right, so that's what we're going to do on the execute. Now our instruction pointer is pointing to 1. And so yeah, so you can see now that we're back up to instruction 1. We're going to fetch that. It's an add 7, and now we're going to repeat. So we're going to add 7. So we're going to take the value in 7. We're going to add it into the accumulator. Then we're going to store 6. We're going to take, this will be a 3. We're going to store it in location 6. And then we're going to jump back to location 1 again. And so this little program is just going to iterate over and over, basically forever, and adding numbers to the accumulator and then writing them out to location 6. So yeah, and that's it. All right, so questions on that? Yeah, that's more or less how your CPU works, yeah? Yeah, yeah, exactly that. The accumulator is just a multi-purpose register, right? So it's just when you make a temporary variable or you want it just holds the value for you as we add stuff to it or whatever. There's a bunch of, this is very simple. There's a bunch of registers. And also, yeah, there's a bunch of caches as well. Like this is essentially what happens, but in reality, to try and speed everything up. Yeah, yeah. Yeah, and you're talking about this cycle here, or you're talking about compiling C code. Yeah, in some sense, you're right. Yeah, it is sort of that. Now, this happens at a hardware level. Incidentally, any program that you write can be, you can also make hardware that does exactly that, right? So there really is software and hardware. There was a saying when I was in school that software and hardware are the same thing. It's not quite true, but it is sort of true. You can hard code anything into hardware and make it run really fast. The nice thing about software is that we can change it, right? So that's, yeah. What's that? Sorry.
What's that behind?
Well, that's memory for us to use, basically. Yeah, you're right. We have a couple of unused locations here. We're going to talk a little, we're going to actually see what happens when we load up a program in terms of memory, but yeah, that's a good question, actually. It kind of leads into what we're doing. Nothing. Again, this is just, this is memory we're allowed to use. So I am reading from location 7 and writing to location 6. I could swap those, that's fine. Right, this is just memory that, so yeah, at the CPU level, there are variables, I guess, in assembly, but when you get right down to it, there's no variables, there's just memory locations, right? So they mimic variables, yeah.
Since we don't use those like memory places like 4, 5, 6, does it release after some point, or do we have to do the?
Yeah. Yeah, so this is a simplification. But yeah, this is like, okay, well, let's move to the next section. We'll try to address those things. Okay, other questions about this or, yeah. Yeah, this is a program, right? So this so your operating system is actually also a program. It used to be actually when you ran a program, it would take over the operating system. The operating system would be gone from, well, it would be stored somewhere, maybe to disk or to RAM or whatever. But now when we run code, there's also the operating system running in the background because everything's multi-threaded and things like that. But yeah, it used to be that when you wanted to run something, things were so simple that basically, if I compiled a program or had a program in memory and tried to run it, it's the only thing running. I've taken over the entire computer. I can basically do whatever I want. Most of the things you would try to do would end in disaster, but if you're careful, you can do some cool stuff. Yeah, sorry. I don't know if I answered the question. Maybe went on a bit of a tangent, but other questions? Yeah. Yeah, this is a very simple version of assembly. Yeah. Yeah. So real assembly gets very complicated, but there are like some assembly languages that you can program in. So yeah, so basically this is known as assembly, and everybody used to write code in assembly. Like it used to be the best thing. Before that was punch cards, which were kind of awful, right? If you drop them, then your program is now, you have to pick it up and figure out what order they were in. And then assembly came along and that was great. And then what happened was along came compilers. People got clever and figured out that, well, as long as I had a language that, sort of had all these constructs, I can compile that into assembly code. So I can write this, I can compile it, the compiler will write this into memory, and then that's what gets run. And then basically this does the same thing, right? So this basically loops forever, adding a single value to X, basically until something bad happens or somebody hits Control C. So yeah, I'm not going to get into the GDB. So if you open up GDB, you can actually see, again, maybe I'll get to it later, but I do want to I am aware of how much stuff we have to cover. But if you do GDB, you run your program, you can actually see the C code and the assembly code at the same time, and you can follow along. You can step through your program step by step and see what's being run, which is kind of cool. For us, we're not going to, I'm not going to test you on assembly, but I want you to have a working model of how these things actually operate, or at least something close to it. Yeah, we're going to skip this stuff. Oh. I'm missing a thing. That's all right. All right. Uh, okay, so to address the memory question, I'm going to sort of, I'm going to update these slides later, but right for now, I'm going to draw some clumsy pictures. Okay, so what happens when we actually allocate, when we run a program? Well, there's 4 main pieces of memory. There might be a reason why I skipped this actually. So let's say you imagine a grid, right? So I have all my memory, it's sort of increasing in the right direction. I go, left to right and down the page, right? So this is just a page of memory. Imagine it's a grid. I'm not going to draw all that in. So what happens is when I run my program, I get this chunk of memory, and how it's allocated is, well, the first location has a jump, and it's going to jump to some location where my program actually starts, right? So let's say that that is here. So I have, right? So yeah, there's a bunch of memory here, and the first instruction is actually here. So the very first instruction when I run my program is a jump to the first instruction of my code. And then the code runs, across here. And I'm sorry for how terrible this drawing is, but so you can imagine all my instructions, all my code is in this part here. All right. And then, so what's in the red part? Well, that's actually my global variables, my string literals, right? If I write a piece of code that does something like this, well, this name Bob is stored somewhere, and it turns out it's stored along with the global variables and static variables and things like that. So there'll be 3 pieces of memory, one that holds a B, or the value that represents B, one that holds an O, and another that holds a B, right? So there's a bunch of information in the red part. My code is in the green part. And then on the other side is the function call stack. So every time I make a function call, like let's say I call main is the first function. So any variables that are in main are going to be stored in this stack frame. And then maybe I make another function call to something called foo, and a bunch of variables will be stored in that stack frame. And this is essentially, yeah, there is a reason why I skipped this. It's a little high level, but yeah, this is essentially how memory is partitioned on startup when you start your program. And then as you call a bunch of procedures or functions, the stack will grow and will shrink when you return from them. And if you ever call too many functions such that the stack actually grows and then overwrites your code, you get a stack overflow, right? So that's what happens there. But yeah, that's kind of maybe getting a little high level for this class, but any questions? Okay. And then yeah, so when you get we're going to see this idea of storing our variables on the stack frame and what can happen coming up, because what I can do is C is not all that safe, which means that I can actually, if I have 2 variables side by side, X and Y, and I can take the pointer to X, I can add 1 to it, and I can actually write a value to Y, or whatever happens to be in that memory location. And if I do that on purpose, great. If I do that by accident, that's a problem, right? Because now I've just sort of stomped on the value Y, and I've set it to something maybe that I didn't expect. And that causes a bug that's really sort of a quiet bug. Right? It doesn't crash right away. It just keeps on running, and then the next time I access Y, I get some wild value, and I have to try and figure out what went wrong. So you'll see that when you write your first assignment, it's using arrays. We're going to talk a little bit about that, but what can often happen is that I can walk off the end of an array, right? My array is size 4. I try to access location 6 in my array, and C will let you do that. Now that's not that memory location does not belong to my array. It belongs to something else, maybe another variable. So if you're not careful with arrays, you can get those weird errors. All right. Questions on that? The heap. Yeah, so I was looking into that. So it used to be that, yes, so this would be my code here. The green would be my code. And then the heap used to traditionally kind of grow in this direction. And then if the heap and the stack met, then you'd run out of memory. I think nowadays, though, from the best of my research, and to be fair, it's probably different for every system, right? So everybody that's implementing this might do it differently. But let's say I want some memory from the heap. I do a malloc, which we're going to talk about later. So I'm telling the operating system, look, I need some memory to store a variable. So malloc me enough memory to store an integer. And basically the operating system will go off and grab me 4 bytes and then return me the memory address of those 4 bytes, right? So I'll have a pointer here that points. So technically, I think the heap is now sort of on most systems apart from this. The nice thing about that is I can always ask for more heap memory and the operating system won't crash, no matter how much I ask for. It might slow down, it might have to start using the disk, but it's pretty resilient to crashing. I can still crash it by calling too many functions, right? So if I make a recursive algorithm, I can get a stack overflow, but calling more heap memory is very flexible. All right, so that's, again, depending on the system you're on, you might get something different than this model, but I think this is pretty good sort of approximation of what happens. Questions, other questions? Okay. All right, so we did the hello world, and that would compile into, I didn't use Vim. I had an idea that I would use Vim for this class, but I'm not sure that would actually slow me down quite a bit because I'm not very good at Vim. But I wanted to try and get better, so maybe I will try it. I guess just to show you what Vim is, if I say Vim hello world.c, I get this. So the nice thing is, if I'm working on OpenStack or on my own computer, Vim's going to work, right? gedit's not really going to work unless you have a desktop. So Vim you can do across an SSH, across a tunnel. And it's not that easy though. By default, well, I don't know what, I don't want to start slamming some keys because it has a bunch of commands. So right now we're in, I think it's called command mode, right? So now if I hit I go into, you can see down here, the insert. Now I'm in insert mode, and basically now I can start editing things. I can go down here and say, hello world again. And then to get out of insert mode, I hit escape, and that takes me back into command mode. And now you can see that, I can navigate around, but if I can type F doesn't do anything. So you can see I'm not in insert mode anymore. So Vim's a little strange. If you know anybody who's good at Vim, they appear to be a wizard, but I'm not. The big question is, how do you now quit Vim? Okay, so Control C might work, but anybody know? This is like literally everybody that uses Vim, yeah, you know?
Colon Q and then.
Yeah, so colon takes me into command mode. And then I'm going to say Q for quit, but I also want to save. So I'm going to write W for write. So WQ, colon WQ takes me out. And now I can compile it again and run it again. And I get, I've changed my code using Vim. So when I first started using Vim, the how you quit Vim always hung me up because it's not that easy, right? You hit I for insert, type away, then you hit escape to get out of insert mode, and then colon WQ. So that's like 4 steps in order to just exit this program. But again, I might try this later, but questions on this? Okay. All right, so you can refer to the slides if you want to know. I know Christine, she claims she's not a Vim wizard, but she does remarkable things with Vim. I'm not anywhere near what she does. So a couple things to note about our first program. We included the standard input output, right? So we wanted to read and write from the console, so we included that. This tells the compiler to include a header file. It's got a .h, and since it's in the standard library, this gets linked automatically. We didn't really talk about linking, but we will. But a header file contains function definitions, type definitions, things like that. In C, we have a main function. If you were writing in Java, of course, you have to have a class, right? You have a class, and then you have a main function within that class. But in C, there's no classes, right? There's only functions. It's an imperative or procedural language. That also means no access modifiers in C. So public, private, and protected do not exist. You have to write carefully, basically. Okay. So printf is a function from the standard input output. So that's what we're going to use primarily to output characters to the console. And that's, you know, if you're interested in the Java equivalent, it's a system.out.println. All right, so this is all stuff that we covered. Okay, so let's look at some other things. So we're going to basically at this point, we're going to cover some basic C programming. And so one of the first things we want to do is, of course, print stuff out to the console, which we already did. We printed hello world, but of course, C has variables like any language, and we want to print those to the console as well. That is not quite so simple, right? So this is sort of a relic of a bygone era, but you can actually, I believe there's a printf in Java where you do basically exactly this. But if I want to, for instance, print an integer, then I'm going to use %, which is this like escape character, D for, I don't know. I don't know what D is for, but for integer. And that's going to take whatever values in this variable and print it out here, right? And then, so D is another integer and %f is for a float. Okay, so we're going to see an example coming up shortly, but, and those are equivalent to, we can use a string.format. I think there's a print format. The typical way to do it in Java is just by concatenating strings, right? And it does all the conversions for you. In C, we don't get any of that. We don't get any of those convenience methods, right? We kind of have to do everything this way. Okay, so there are a lot of different, you know, the % symbol is for printing formatted data, and there's a lot of, I guess, properties that we can invoke, right? So there's the width, there's the precision, which is a dot precision, there's the length. Actually, I'm not sure what the length is, how that's different from the width. And a bunch of flags. Okay, so let's take a look at some of them. I think for this, the best, and again, this is, yeah. What are flags? So right here, I have the % symbol and the D would be considered the flag, right? So I'm saying the % is telling the print that this is going to be some value I'm going to provide you. And the flag D tells it how to interpret that value and how to output it to the screen, how to change it into characters, basically. And I have to look this stuff up all the time. Okay, so it's not easy to remember. Of course, %D is sort of easy. It's just an integer, and that's %D and %F will probably be the ones that you use most often. But there's a bunch of other things like unsigned integer, floating point. By default, that gives you, yeah, all right, let's go to the example, and probably easier to do it that way. Oh, yeah. First, let's upload the example. Okay. And printf. So here we can see, Okay, well. Going to comment all that out. And so the first example, we have an int average is 10, an int a is 20, and a float that is 200. So we can print out the average with a %d. And you'll notice that, well, let's run it. GCC-o printf printf.c. Oh yeah, sorry. I was fooling around with it earlier. Oh, I didn't save it. Okay, so then printf. Yeah, the average is 10 hours. Joe is 26 years old and weighs 200 pounds. So we can see there's a little bit of formatting there. We can also see that even though I have two separate printfs, it's not like print line in Java, right? So I have to explicitly add in this new line. And if I don't, then this string and this string are both written to the same line. So %d, I think, is pretty straightforward. That's your integer. When I write out a float, you might see often something like this. So the 0.2 means I want, for floats at least, it means different things for different flags. But for floats, it means 2 decimal precision. Okay. So you can see when I ran the code, I had, when I ran the code, it said 200.00. Okay, so I can specify all that by these flags. All right. So, and yeah, it's, if I put the % twice, then I have to provide 2 arguments separated by commas, and they should match, whatever the format I called for. You can, of course, swap certain things in C, like you can swap a char for an int and things like that. Yeah, questions? Okay, so this is, I mean, we'll go through a little bit of the examples. I don't expect you to memorize all this, but just so you have some idea of how it works. So %f, if I don't put any precision, I think it defaults to 6. Now let's see what it does actually. Again, because I don't. If I use this, I am almost certainly going to have to look it up. So if we match this up to, well, all right. So this is the %f, and it, yeah, so we did 6 units of precision here. This one added some zeros. So we did 6 decimals of precision by default. Okay, so if I don't put the 0.2 here, oops, I mean here, then I'm going to get 6 decimals by default. G is, well, let's see. Floating point exponent precision, right? So yeah, if I put, well, again, I'm not very good at exponents either, but if you want scientific notation, you're going to use the %g. I'm going to sort of steer away from that and stick to the main ones, which are the character. So that is %c for a single character. If I want a string, it's %s. And, there's some hexadecimal and things like that, which we're going to come in handy when we get to that one. But for now, we can focus on %d, which is decimal, %d, which is integer, %f, which is floating point, character, and string. And we'll mostly stick to those. All right. Anything interesting in that example? Yeah, so you can see that I didn't use the point. The point is for precision, but I put a 5 here. And what that's going to do is it's going to pad it with 5 locations. Okay, so you can see 256, it's 3, and there's 2 spaces before it, right? So when I put 5 with no decimal, that means I want, whatever it is, I want it to take up at least 5 spaces, right? So if I embed this in another string, then I can, I can sort of write a table or something like that by making sure it has some precise width. Yeah, and you can do the same thing with strings. And floats. So I'm not going to cover that. This is the sort of stuff, again, if you really want to know, you can Google, but it's easier to sort of learn by doing with this stuff. I can also indicate both a precision and a width that I want it to take up. So this number should be 3 decimal places and take up 7 spaces altogether, right? So this 3.142, this is 5 spaces, and then I have 2 blanks before it. Okay, so I can specify all of those things. I think that's about all we're going to cover for now. And you can do the same thing with, right? This is hexadecimal capital, but we'll pay more attention to that when we get to hexadecimal. The minus flag lets you left align it. So you saw by default that I had space to the left of mine. If I put a minus in front of it, it would have aligned it to the left. So the words would have been to the left and I would have my 2 spaces on the right. So that's all that does. All right, so I'm not going to spend too much time. Do play with it, figure some of this stuff out on your own, but questions? Okay. Again, I mean, I find when I have to use it, I have to look it up no matter what. So C has 4 main variable types, right? So there's not a lot of, again, it is very close to what a computer actually does. And a lot of these types are actually very similar. So we have an int, we have a char, we have a short int, and we have a long int. And really, these are all versions of the same thing, right? These are just sort of magnitude only, or, these are values. So the char is 1 byte. The short int is 2 bytes. The int is 4 bytes. This might be different on different systems, but by default, these are mostly what they are. And the long int is 8 bytes. Okay, so, and these are all basically just numbers. If I wanted decimals, I'm going to use a float or a double. So a float usually by default is 4 bytes. A double is 8 bytes. And that's it. That's basically the main variable types in C. So character is essentially a number, but it's a special kind of number where when we print one to the screen, it converts it into a letter, right? So it just does a table lookup. But we can treat it just like a number. We can add to it. We can subtract from it. We can multiply. We can do all of those things. You'll notice that if we compare it to Java, well, the first thing that comes up is Java has a Boolean and C does not. Okay, C, when we can sort of fake a Boolean or imitate a Boolean, as we'll see shortly. The other thing, if I want to declare constants in Java, I use the final keyword. In C, the sort of recommended way is by using preprocessor constants. So I use the define, and then I write whatever my constant is, and then whatever value I want to represent. And it's very simple how this is implemented. It goes through your code. It finds all instances of this. And it just replaces it with that. So there's a preprocessor when we compile, it goes through and it first does that. So everywhere where you see days in a year, it's going to replace that with 365 and then it compiles it, right? So very, very simple. There are if and switch statements that are basically, these are basically Java adopted C's syntax. So it's going to seem very familiar if you're familiar with Java. But we can do stuff like this. If the grade is greater than or equal to 80, and less than or equal to 100, then we print out something, encouraging. This is without braces here. And if I do it without braces, it's just going to look at the first line following the if statement, right? So if I had a second print here, and I don't have the braces, it's only going to do the first one if my grade is between 80 and 100, right? If I want to put more lines, I'm going to use the braces to indicate that it's a block of code. So in this case, if my grade is greater than or equal to 50, it's going to print these 2 lines. And then, of course, the else condition. If this turns out to be false, then I'm going to print my grade is too low. Okay, so that's should be sort of familiar. Switch statements might be something else that we're going to use. Again, the syntax is basically the same on a lot of languages, but this is exactly what you'd see in Java. Booleans. So in C, we fake Booleans. Basically, everything's a value. It's either a decimal or, an integer. Even a character is just an integer with only, only 1 byte. But if I want to fake a Boolean, I'm going to just supply a value. And so the rule of thumb is that if my value is 0, that's a false, and anything else is true. Okay, so I can use, in this case, a char because it's the smallest thing. So it's only 1 byte. So then I can use these chars in place of Booleans and, basically say, well, if this is true, print I give up. And this is going to evaluate to true if this evaluates to not 0, anything but 0. And we can see some Boolean operators here. We're going to get into more detail on that. But if I go, yeah, and in Java, of course, we have a Boolean type that we can use. The not operator, we get that in Java as well. Here, what it's going to do is it's going to change the value. So whether I use an int or a char or even a float to indicate true or false, if I put not tired and tired is anything but 0, it's going to be turned to 0. And if I put not tired and tired is 0, it's going to be a 1. So in this case, if I put not sick, sick is 0, sick is now going to be a 1. And this happens even if sick is a float, right? If I do this, this still returns a 1, and it's not a float, right? It's simply it's in some sense a Boolean value, but I could assign it to an int or a char or a short int or something like that, but I couldn't assign it back to a float. Like I can't do if I have, I think I can prove that. That's sort of a weird little effect, but if I said something like this, float tired equals let's make that 0 actually. See if I'm lying to you. Yeah, maybe it does work. Okay, no, this is straightforward. Sorry, there was a well, there's a scenario where this fails, but I forget where it is now. So I guess in this case, that's okay. So I can assign 1 to a float value, but maybe it was in a math operation. Anyway, so not tired actually returns an int value or a character value. So yeah, programming example. So if we want to fake Booleans, which this is sort of, the suggested way to do it, we're going to define true and false to be 1 and 0, right, using preprocessor constants. And then we can assign our characters, sick and tired, to either true or false and then we can test them using the if statement or using the, what do you call that? Conditional operator. So, all right, so tired. So yeah, says, well, if I'm tired, then print tired, otherwise print not tired, and I've set tired to true, which is 1, so that evaluates to true. If I put sick here, then this should say not tired. Right. Okay. So yeah, Boolean values, we fake them, but there's a pretty, well-established way to do it, and that's we make these preprocessor constants. And yeah, questions on that? Yeah.
0.01, is that going to be false?
Yeah, 0.01 is going to be true, right? So yeah, that's a good question. Let's make sure it compiles first of all. Right, so yeah, if it's true, you know what I think it was? Anyway, the place where it went wrong was I'll come back to that, but yeah, true and tired. So here it's true 0.01. So yeah, anything but 0. And if I do a float value of 0, this is still going to be false. Okay. Other questions? Yeah. Yeah, so this is the conditional operator, right? So that is this. And what it is it's basically an if statement that's an expression. So it's an if statement. So this if statement says if this is true, then execute some code. This says if I have some Boolean here and it's true, I'm going to return a value, right? And if it's false, I'm going to return this value. So if runs code, the conditional returns values. Yeah. Other questions? Okay. Yes, I do remember where this failed before with the, I'm not going to get into it. Which time we got? Yeah, if you do a printf, let's say I do %f, and then I do not 0.0. Was this it maybe? Yeah, it doesn't like that. It just gives me a warning though, because technically this returns an int, right? So yeah, if I say not to a float, it turns it to an int, but of course I can still assign that to a float because there's some automatic conversions happening, but in this case, it gives me a warning. All right. Loops in C, again, these are very similar to what you would have seen in Java. So a simple for loop. I declare the variable inside the, the for clause. So this is the variable, the condition, and then the increment. And I can also do while loops in C, and yeah, while loops again, but also do while loops, which I don't remember the last time I used the do while loop, but essentially a do while loop is going to guarantee that this is run at least once. Okay, so a while loop might not run at all if this evaluates the false right away, but a do while loop always evaluates at least once. All right. Now, because we're writing technically system level code, we want to be efficient. So one of the things we can do to be efficient are to use the break and or continue keywords. So break will break out of a for loop. And it'll basically, if you're in a nested for loop, it's going to break out of one level, right? And continue will not break out of a for loop, but it'll jump to the next iteration of the for loop. So maybe I'm doing some calculations inside the for loop, and if I figure out, here I'm testing to see if a number is prime. And so as soon as it's divisible by something, I know that it's not prime, at which case I'm going to break out of this loop and then print out that it's not prime. Or I guess in this case, I'm going to print it is prime if it is prime, and print nothing if it's not prime. On the other hand, if I wanted to stay into the loop, but in my current iteration, I'm done with whatever calculations I'm using, then I'm going to use continue, and it's going to jump back to the top of the loop and enter the next iteration. Okay, so these are two things that we can help to make our code more efficient. Yeah, so this is an example of continue. Right, so if I'm looking through resumes and I'm HR, I'm trying to find somebody to hire. If they have less than 2 years of experience, then I'm done. I want to go to the next person. So I hit continue. If they do not have the necessary skills, then I also want to exit this. Otherwise, I want to keep going and keep looking at to see if this resume is okay. All right. Math and operators. So, well, arithmetic operators and relational operators, these return Booleans. Bitwise operators, which we are going to get into, which are a lot of fun, but difficult to work with. So yeah, if I do math, I have to remember the order of operations. So I believe I have, yeah, we do have an example of that. So the order of operations is going to affect things. Well, actually, let's just jump to the example. So I have 3 ints x, y, and z, and I assign 4 to x, and I assign the value in x to y. So now x and y are both 4. And then I try to evaluate this. And for now, I'm just going to comment that out. So you have to be careful with this because in C, as in a lot of other languages, it does follow BEDMAS, so brackets, exponents, BEDMAS, division, multiplication, addition, and subtraction. So it's going to do this operation before it does this operation. So it's not going to be evaluated left to right. If it was evaluated left to right, we would have y plus 2, which is 6, times 4, which is 24, minus 3, which is 19. But when we do run it, we get 9, right? Because this gets evaluated first. So 2 times 4 is 8, and then plus 4 is 12, minus 3 is 9, right? So order of operations, when in doubt, just use brackets. I guess some other interesting things we can do. We have the minus equals times equals. So this means that I take the value x, I subtract it from z, and I store the result back in z. And that also applies to multiplication, division, and addition, right? So this minus equals, plus equals, times equals, that's how they work. I can chain a bunch of operators together, in this case, assignment operators. And if I do that, well, traditionally, if I'm doing a math expression and everything has the same precedence, like it's a bunch of, I add this plus this plus this, then I'm going to go from left to right. But here this goes from right to left. So I'm going to execute this first. So I'm going to assign the value 7 to y, and then I'm going to assign whatever values in y to x. Okay, so these operators do kind of, they have their own precedence rules, and they have this, I forget the name of it, but basically whether you evaluate left to right or right to left. There's also these prefix and postfix rules. So if I do, so I'm going to, all right. Okay, so I have a value x, and then I'm going to run a bunch of operations on it. And these operations are a little bit special in that I can embed them as values, right? So this means increment x and then return the value that the new value of x. So if we look at the original value was 7, I increment x to 8, and then it returns 8 and prints it out here. And then you can see that, yes, currently my x is at 8. The postfix operator, so x++, actually works a little bit differently. So it does increment x, but when it returns a value, it returns the old value of x. Or in some sense, you could think of it as it returns x and then increments it. So yeah, this one is a little more efficient, but it's not something we're really going to worry about. Things like for loops and things like that, it doesn't matter which one you use because it's not embedded in an expression. Only when it's in an expression does it matter whether you use x++ or ++x. All right, questions? Okay. Yeah, all of that hopefully is pretty straightforward. Oh yeah, we also have the math library. So in this case, trig. So for the math, you'll notice that I didn't need any math library. So I would normally include math.h if I needed some math stuff, but just for regular, arithmetic operations, I don't need the math library. But if I go into trig, I do need the math library. So I'm going to include math.h, and then I have access to these functions. So sine, cos, tan. I've defined a preprocessor constant pi, which apparently, I guess doesn't come with the math library. I'll have to look that up. But ceiling, floor, power, absolute. This is return the absolute value as a float. But let's say I wanted to execute that now. I'm going to compile it into trig. And it says undefined reference to cos, undefined reference to tan, undefined reference to sine, right? So even though these things are in the math library, you can see that my compiler is not complaining. It's not working. So what happened is that we haven't really gotten to functions so much yet, but this only contains function definitions. I'm just telling the compiler, look, there is a function called sine, and I can give it a float value, and it will return a float value, right? And that's all the compiler needs to know in order to tell me that, yes, I'm using this correctly, so this will compile. But what it doesn't have is any of the code that goes into this function. So the math library just tells me what functions are available. The actual code for this library exists somewhere else, and I have to what's called link it to my executable. Okay, so I'm going to run the same command, but now I know I have this math library that only has the definitions. So this -L means library and M for math. So this is going to take the source code for that math library and link it to my code. So now when the compiler goes through, it says, yes, there is a function called sine. I know that you're using it correctly, but also because I linked the library, it also has the source code now. So now I can run trig. Oops. All right, so then all of that works. So you'll notice we talked a little bit about compiling to object code. So if I did something like this, let's say I left that library out, and then I'm going to compile it to trig.o, right? So, and the compiler is okay with that because I can't execute trig.o. What I've done is I've compiled my work, and then the compiler says, well, that's fine. I know you're using these correctly. I don't have the code for it yet, but you're only compiling to an object file, so that's okay. So when I link it, I have to give it the code. So then I can do a second step, gcc.o trig.o, which I just compiled. And then I'm also going to link the math library. And then I get my executable. Okay, so there's a lot of libraries in C and C++ that are, you're gonna have to link them. You get when you put the header in, you get the definitions, and then the compiler knows enough to compile your code, but you don't actually have the implementations. Is there a question? Yeah. Yeah, well, no, I'm assuming. Let's see here. Well, I know G is for scientific notation, so I'm guessing that's just a, so if I do 0.2, oops. No, nothing, huh? Yeah, well, G is scientific notation. I think this, let me just do this, just to make absolutely sure that this is a float. No, you're right. So it's not float absolute. It's I don't know, would have to look it up actually. So yeah. Yeah. Other questions? Yeah.
Do we have to compile it? So, for instance, like you did LM for the math library.
Yep.
So you use 3-4 for their library.
Like you have to link them all? Yeah. Unfortunately, but as you'll see later in the course, they have build tools for that, right? Like so a make file, which as you add libraries, you just add it to the make file and then everything compiles correctly. But for now, yes, if you have multiple libraries, you have to link them all. So when we get to graphics, you'll have to link like the X11 library. Other questions? Okay. Yeah, so that's that example. Random numbers, so we'll quickly talk about those. So the interesting thing about random numbers is that so they're in the standard. Yeah, so here I'm going to generate a random number. I'm going to divide by the maximum so that I get a percentage, right? Otherwise, it's just going to just return a number between, what is it? A number between 0 and this number. But if I want a percentage, I can divide by this rand max number, and then I can get a percentage. So I can do something like UCC-O rand. Rand test. Okay, and I can print out a bunch of, here I printed out 10 random numbers as floats. And then if I run it again, I print out 10 random numbers as floats, and then I run it again, and I print out 10 random numbers. And anybody notice anything strange happening here? Same sequence, yeah. So maybe you guys are familiar with this idea, but so when I make a random number, of course, if I don't seed this, I'm going to get the same sequence every time, right? So these are pseudo-random numbers, which is basically just a list of numbers in this order that looks kind of random. And if I don't tell it, please start somewhere other than the beginning, I'm just going to get the same sequence every time. So then I can do something like this, where I can seed the value. And then in this case, I'm actually printing out decimals. But I've seeded it with a value, which means I'm going to get a slightly different sequence of random numbers, which you can't really see here, but if I change it to 2. So I had it seeded at 1, and I got the same sequence of random numbers twice. So now I seed it at 2, and I get a different sequence of random numbers. So this is nice for debugging. When I have something random in my code, if I give it the same seed every time, I'm going to get the same sequence of random numbers, and then you can figure out, right, as soon as you find a seed that causes your program to crash, you keep it and track down the error. Right? So that's very handy for that. Otherwise, I really want things to behave randomly. So what I'm going to do is I'm going to seed it with the time. This returns the number of seconds since 1900 or something like that. So every second, you're going to get a different sequence of random numbers. If I run the program twice in a row really fast, I'll get the same sequence, but otherwise I'll get something unique. So yeah, that's random numbers. So that's it for today. We will pick up on Thursday, continue talking about this, and then get to something else. Hey.
I would say I